Yes, hello, Mr. Sushan Lal Babu. Welcome on your media platform, and let's start your snap for heat transfer. As you mentioned,
No, sorry, it's a CMERI, Mechanical Engineering
CME.
Research yes,
Yeah,
Research Institute.
good, good, fine. So let's start with your heat transfer snap. So I'm going to start with the first very simple question. What is the mode? How actually convection takes place? What is the mechanism of convection heat transfer?
Sir, convection we can split into advection plus diffusion.
Hmm.
And advection means the flow of bulk motion of the fluid, heat transfer happening because of the bulk motion of the fluid. And
Hmm.
diffusion, we can explain it as the molecular level. That means from higher concentration to lower concentration, the molecules are random molecules motion happening. Then it can be termed as diffusion. And always convection is preceded by conduction. It is not an independent mode of heat transfer.
So in fins, convection takes place, conduction takes place, or radiation. Which mode actually dominates?
uh, in fins, always conduction is there and convection is there. So any substance which is higher than the absolute 0 Kelvin, then definitely radiation also will be there. And mostly in fins, convection dominates.
Convection
After
is going to
after
dominate.
conduction, the convection we are using fins for enhancing heat transfer through convection mode.
Krishna, suppose let me give you a case. Suppose there is a weight, something like that. You know, in winters we rub our hands to get some kind of heat. Okay.
Yes, sir.
So
Yes,
suppose there are two surfaces. I'm giving you the one, the bottom surface is fixed. The
yes,
upper
sir.
surface is having some mass. You can consider it like a 2.5 kg. धर्मेंद्र जैसे शनिदोल बोलते हैं ना 2.5 किलो का हाथ. So something like that. It is 2.5 kg hand, and we are rubbing over some surface.
Okay.
Okay.
Yes,
And the
sir.
coefficient of friction also you can assume.
Okay.
Now you can you give me how much heat we are generating in that process?
Oh, sir, because of the rubbing
Mm-hmm.
friction, sir, sorry, sir, exactly, I am not getting
Okay.
the
Try
concept.
to think like some work we are doing obviously to.
Yes, sir. Yeah, we are doing work.
Mhm.
Uh,
So that entire work is converting into heat only.
yes, sir.
So think
If
of
there is,
the work,
uh,
because finally that work, entire work, whatever we are doing, that is converting into heat energy. Some part our body is
what,
absorbing,
sir,
some part
what,
is going to the surrounding.
yes, sir, force into distance,
Hmm.
sir, if we get the frictional force, once we move the hand forward, the friction force that will be, we can calculate the friction force from the normal reaction into the coefficient of friction,
Hmm.
and that fraction from force into distance traveled in one direction can be referred to as work done by the hand of 2.5 kg, and that work will be transferred into heat. That energy might be converted into heat when we drop over the surface, stationary surface. That
Hmm.
what I am thinking, sir.
You heard about steady state heat transfer?
Yes, sir. Steady state means the temperature variation independent of time.
Hmm.
That means, yeah, it's independent of time. That is steady state. With respect to time, there won't be any change.
Means what is independent time? Temperature
Uh,
or heat transfer
Temperature,
or
sir.
what?
Temperature.
Hmm. So steady state heat transfer from one body to another body, suppose, is a kind of reversible process or irreversible process.
It's a irreversible process, I think, sir.
Why?
Because steady state means whatever heat entering to, suppose if you are considering some body and the heat is entering at one side and heat is leaving at another side, to
Hmm.
be that body has to be in steady state, the how much quantity of heat entering has to be same quantity as to be released. And but anyway there is heat transfer happening, so it is a reversible process. So irreversible means the heat transfer has to happen in between infinitesimally small temperature difference, or or it has to happen at within infinitesimally small time. So both these two cases are, I think it's no ideal situations. But in
Mhm.
real case, a steady state heat transfer happening in steady state means it's reversible process only.
Fine. So let us consider, a kind of blades of a turbine.
Okay, sir.
So some steam or some hot gases are entering into the turbine, and heat transfer is taking place between that hot stream and the blades of the turbine.
Yes, sir.
So how you can model that particular case?
So first I can calculate, I can get the temperature, inlet temperature, or we can consider blade as a system, and the
Mhm.
air flowing over the system around the blade can be a surrounding. That means surrounding temperature we will get. That means air temperature or free stream air temperature we will get,
Mhm.
and the blade surface temperature also we can, if we get, then uh, the convection through from the air to blade, heat will transfer through convection mode. So that depending upon the heat transfer coefficient, area exposed to the free stream, and the temperature difference between the free stream and the blade, we can calculate Q transferred to the blade.
So that will be a kind of steady state heat transfer or unsteady state heat transfer.
That is a steady state heat transfer, sir.
So how you will ensure actually the system reached some steady state?
Yes, sir. Sir, at the beginning, definitely it will be unsteady because the temperature of the blade will be at, maybe you can assume it as atmospheric condition.
Mhm.
So if we have to leave, if we leave that particular situation for some time or some hours,
Mhm.
after that is the it will become steady. Till that time it will be a transient. The temperature slowly increases, the blade temperature slowly increases, and it will reach an equilibrium condition after some time. Then we can say that it is in steady state. The temperature won't change after that, beyond that time.
So suppose there is a kind of hot steam, hot air is flowing over a cold surface, solid cold surface.
Okay, sir.
You can consider that solid surface like a flat plate.
Okay, sir.
So can you give me some kind of temperature profile over that?
Yes, sir. It will be parabolic.
Mm-hmm.
Uh, Hot surface to cold surface, the temperature variation means
The, the stream is hot, the surface is
oh,
cold. So it is a
sir.
kind of
Okay,
cooling process, we can say, cooling process.
cooling process. Okay, sir. Sir, it is if, sir, I can say if the surface is hot and air is cold, then it will be
Mhm.
like inverse of the what velocity profile, or a mirror image of the velocity profile we will get if the surface is hot and say airstream is cold. So when we consider the surface as cold and air as hot, then it will be
Mhm.
the, that it will come in the opposite direction, reverse direction.
Usually, what kind of temperature profile we assume?
Sir, as per my knowledge, it's parabolic, I think, similar to velocity profile. I think, sir.
It's parabolic. Mm, okay. So, what do you understand by thermally developed flow?
Thermally developed flow means that profile, once it becomes um, uniform throughout the cross section,
Mm-hmm.
then we can say that thermally fully developed flow. The temperature profile becomes uniform after particular length. So from afterward, till then it is developing, and afterwards we can refer to as fully developed.
Mm-hmm. So here, uh, the blades are like the the cold plates, and the steam is the hot fluid, and the heat transfer is taking place between them. So how you
Yes,
will
sir.
model that case to find out the rate of heat transfer? Just give me some idea how you will find out the rate of heat transfer for a single one blade.
Sir,
You can go with some steady state condition. Some suppose we are carrying out some heat removal. Okay, generally we attach such kind of system, some kind of cooling system we provide
yes, sir.
inside
Yes, sir.
the
Yes, sir.
turbine medium, and suppose
Correct.
through that we are maintaining some constant surface temperature, means the uh, blade temperature, and the stream temperature is also constant because that stream is coming out from some kind of source, maybe combustion chamber or some boiler. Okay.
Yes, sir, I got it.
Now
Yes.
think of how you will find out the heat transfer.
Sir, if we consider in that situation, then we have to first from the hot stream to the blade through convection, the heat transfer will take place,
Hmm.
and from the blade outer surface to the blade's inner surface, conduction heat transfer will take place, and within the blade, if there is any cooling channel, cooling flow is happening, then from the inner blade surface to the coolant through convection mode, heat transfer will take place. So if considering three modes and considering calculating the resistance offered by the three different modes, we can calculate the heat transfer rate of heat transfer happening.
The question is
Uh,
like this, Shushan. Question is like this. Actually, our aim is to maintain some circulation of coolant, circulation of fluid inside the blade, so that we will be able to maintain some constant permissible temperature of the blade. Okay.
yes,
So
sir.
the case is like that. The streams are coming at a very high temperature. Suppose uh, it may be suppose 600 degrees Celsius. Okay, the
Sure,
hot
sir.
fluid which is coming, and the blade temperature we want in a range of suppose 300 degrees Celsius, not more than
Sure.
that.
Okay, sir.
So remaining all any dimensions you can consider, some of the dimensions. So what is our aim? We are interested in finding out at what flow rate we will circulate the coolant inside the turbine, so that we will be able to maintain the temperature of the blade in the permissible limits. Obviously, for that some heat transfer is required. So that I asked you how you will proceed to find out that.
So rate of heat transfer, sir, by we our objective is to keep the temperature of the blade constant as 300. So uh, how much heat the coolant can extract per second? That means heat transfer that extract to keep the blade surface 300 degrees
So
Celsius. That will
in steady state, we can say whatever heat is entering, that will be the heat lost by the body.
yes,
So
sir.
whatever heat is going to enter into the blade, that will be is required to be removed by the coolant.
Yes, sir. Sure, sir.
Okay. So now, can you think of this?
Sir, that I am confused with the rate and heat transfer. I know so the equation of heat is okay, but rate at which the heat is transferring Q dot, sir. I am not able to connect to that, sir.
Fine. In fins, we go with some parameter which defines the efficiency performance of a fin.
Yes, sir.
So those two parameters are effectiveness and efficiency. So can you differentiate between them, efficiency and effectiveness of a fin?
Sir, sure, sir. Efficiency, we can calculate by it is the ratio of Q actual to the Q max efficiency, and effectiveness is Q fin with the to ratio between Q fin and Q without fin. So this way we can differentiate both efficiency and effectiveness of the fin, sir.
Acha, just tell me how we can improve the efficiency and effectiveness.
Sir, efficiency can be improved in both cases. The efficiency as well as effectiveness can be improved by increasing the thermal conductivity.
Mm-hmm.
And if I say effectiveness, then from the equation we can conclude that for higher K value and lower H value uh, and higher width, that means perimeter, I think has to be high for increasing the effectiveness of the fin. Effect fin will be more effective for lower H value. That's why we are using prefer fin in a medium of air rather than water.
Mm-hmm. Acha, suppose we are having a cup of tea, na?
Yes, sir.
So cup of tea, there is some hot fluid in that. Tea is there, hot tea.
Okay,
So
sir.
जो cup handle है, the handle you can assume it like a surface which is attached to hot bodies. So that
Okay.
handle of the cup you can consider like a fin. But there is a slight difference. In fin, generally one surface is attached to the root, hot
Yes.
surface, and
Yes,
the
sir.
another is what you can say, the open introduced to the air.
Yes,
But
sir.
here both the two ends
Yes, sir.
are connected to the hot surface. Are you getting some idea?
Sir, actually, sir,
So
different from.
so it's something like that. There is a kind of hot cylindrical body, okay,
Sir.
and some handle is connected.
Yes, sir.
That handle is working like a fin, for example.
So yeah, I got it, sir. So mostly the teacup will be made of low thermal conductivity material.
Ah,
So
fine. Don't forget about ceramic cups. You can consider
oh,
a kind of metallic cup. Okay. So
okay,
we are,
sir.
we are we are just considering it like a case. So there is a cylindrical hot surface, something like
Ah,
this.
yes, sir.
Some handle is connected. Some
Yes, sir.
steel, some good metallic conductor handle is connected. So for that case, I just want to know the boundary condition. How you will write the boundary condition and the energy balance equation. I hope you got the question. It is something
Yeah,
like this.
yes, I got it, sir.
Something
I
like
got it.
this. This is a kind of hot surface. Okay, kind of hot surface like this. Let me put it here. This is a kind of hot surface. Okay, like this
Yes,
here it is a hot surface, and here one handle is there, another handle is there, and one handle is connected.
I
Then you
got
need
it,
to
sir.
find out.
Sir, that is the actually I think it can be referred or related to the fin in finite length fin where convection happening at the tip.
Now,
That boundary.
how you will write the boundary conditions?
That is what I am, sir. That is there are mainly, sorry, sir. I can I refer to that three boundary conditions we are using to solve the equation of fin. So any from that three conditions either because I can relate to the uh, third boundary condition, third case where the finite length fin with convection at the tip.
Hmm.
But you are saying that it is at the, sir, if it is a metallic body, that
Hmm.
handle is a metallic body, definitely heat will conduct it till the tip. And there also one that both bottom and top metallic body is connected at the tip.
So
With
actually,
this,
both from both the sides, heat is going to enter from this side
yeah,
also,
both
this side
from
also.
yes, this side also both
Hmm.
side heat is going to enter, and that will be convected, sir. That will
Yes,
be
yes.
convected, yeah,
Obviously,
sir.
obviously, yes.
Sir, definitely it will act like a two fin.
Hmm.
I am assuming it as a two fin.
Hmm.
So we can, the boundary condition is whatever heat reaches at the tip is convected. Whatever reaches through conduction at till the tip will be convected out. So that is one boundary condition I have gone through. So I can relate to that.
Hmm.
That is what I am thinking, sir. Further, I'm not getting any idea what exactly you mean.
Fine, fine. So you heard about shape factor in radiation.
Yes, sir. Yes, sir. I
What's
have
the
no. Yeah.
what is the significance of that shape factor?
How many, sir? How much radiations? If you consider two surfaces, and
Hmm?
if how much radiation ejecting from one surfaces, and it's a ratio between the uh, uh, how much heat and total heat received by the other surface to the how much heat ejected by the source surface. That is called shape factor.
Mm-hmm. Fine. So on on what factor actually it depends? Shape factor, view factor, or configuration factor?
Sorry, sir, I am not able to say because I don't
So
have clear idea between
it
both
depends
these
on
three.
material. It depends on
Um, yes, sir. This emissivity of the material definitely it depends, sir. Sir.
shape factor. What about shape factor?
Shape factor, surface area, it will
Mm-hmm.
depend, sir.
Okay. So
Surface area and the medium,
mhm.
it depends, sir.
So
Sir, no.
now at last, you can tell me brief about your PhD work, no? So that,
Uh,
because initially we don't had, I think more than 3 4 days ago, I think even more than, I think 5 5 days
yes,
ago,
sir.
you appeared in some snap.
Yes, sir.
So tell me brief about your PhD work.
Sir, actually, I did my PhD on the interaction between the purge flow and mainstream flow in between a blade passage. So,
Mm-hmm.
we this a gas turbine. Exactly, mainly the gas turbine consists of major three components. One is compressor, the other one is combustion chamber, and third one is turbine, where the work is generated. And in turbine I did all my work. And in turbine, if we go deep into that, there will be multiple stages. So there may be three stages, and each stages will be of one set of rotor and one set of stator. And in
Mm-hmm.
that, that number of total, let's say it will be total number of rotor blades will be 20, and the total number of stator blades will be 17 or 18. So I have considered only a single passage between two adjacent plates.
Mm-hmm.
So when the direct gas from the combustion chamber, hot, high pressure, high temperature gas enters into the turbine, definitely it can, if the inlet temperature is beyond the material melting point of these turbine components, it will deteriorate the turbine parts, that blade. So for isolating these blades from the incoming hot gas, we have to provide cooling. And as you mentioned earlier, same coolant I have used, means cooling flow I have used for cooling the turbine blade, but it is an external cooling, not internal cooling.
Mm-hmm.
um, the coolant will be circulated over around, it means it will create a small thin film over the blade surface, and it will be
Then how
isolated.
you provided some passages for that?
Yes, sir. There in a stage, for the smooth rotation of this rotor, there is a gap in between the rotor and stator. So through
Mm-hmm.
that gap, we are feeding or supplying the coolant.
Mm-hmm.
So that gap is called as wheel space. That means, yes, through that wheel space, that the coolant which is directly extracted from the compressor is supplied through that gap. That means it won't, that coolant gas will bypass the combustion chamber. So the temperature will be less compared to the gas coming from combustion chamber. So that gas is fed through this gap. It will eject out of this gap, and it will spread over the blade surfaces and the involved surfaces. So while it's entering into the mainstream or into the passage, the coolant will interact with the mainstream flow. And general condition itself, because the flow is happening around the blade curvature, there is a chance of secondary flows. And because of the pressure gradient between the both surfaces of the blades, so because of that, secondary flows, secondary vortices will be generated.
Mm-hmm.
But additionally, when we supply this coolant, this additional interaction will enhance the secondary losses. So the vortices will become more strengthened. So in the first phase, I analyzed what kind of additional loss vortices are generated because of the interaction of between the coolant flow and the mainstream flow. And in the second phase, I implemented a loss reduction technique called envolve contouring. And that envolve contouring means, normally the envolve will be flat. Envolve means the bottom side of the where the blades are mounted. In between the
Mm-hmm.
passage, it will be flat. But in contour envolve means that instead of flat, it will be profiled. It consists of different hills and valleys, curve that. So the intention of providing hills and valleys is that whenever flow occurs over the hill or top portion, it will accelerate. When it accelerates, the static pressure reduced there. So likewise, we can control the gradient, pressure gradient over the envelope. So the secondary flow will happen mainly because of the pressure gradient over the envelope. If
Mm-hmm.
we counteract, we are able to generate the reduce the high pressure region, means reduce static pressure over the pressure surface, and if we are able to increase the static pressure over the suction surface, then we can reduce the pressure gradient by implementing these hills or contour envelope. So that I tried, and I analyzed 3 different models of involved contouring, and out of that I concluded with which model works more what successful in reducing the secondary losses generated.
Mm-hmm.
That was the second phase. How much the loss reduction can be achieved even in the presence of purge flow or coolant flow by using the involved contouring.
Got the point. Initially, actually, I thought because initially I have not asked you about your work,
Yes, sir.
but only you mentioned about that I worked on some turbine related, some heat transfer related work you carried out.
Yes, sir.
So that's why I asked you those questions. Okay.
Okay, sir.
So ठीक है अभी Shushan, you are looking comfortable, but yes, some more details you need to go through.
Yes, sir.
Actually, internal cooling is more efficient, but yes, it is much complex also. It is difficult to provide the internal cooling system in turbine. But why actually you opted for external cooling?
Sir,
And
yes, sir. Sir,
then
actually,
what kind of results you got? Yes, yes.
yes, sir. Sir, that's a question, but it's a tricky question. If I answer, it's the honestly speaking, in our laboratory, it's difficult to create that internal cooling.
Mm-hmm.
Actually, that setup not available there.
Mm-hmm.
So, in academic purpose, the, because of the shortage of fund, we won't be able to go for high-end experiments.
Mm-hmm.
So because of that only, I restricted that to the external cooling. External
Mm-hmm.
cooling is easy because no need to manufacture a blade with
Yes.
internal channels.
Mm-hmm.
Normal conventional blade can be used for that. That's the
Yes.
main, because if I answer this, then the interview board will think that something negative on me. So how can I answer that question the right way?
Mm-hmm.
So that is
That I think some of the researches are available in external cooling also, but the real system which you are having, those are internally cooled only. So what you can say, sir, actually I got this opportunity to work on this particular area. So I thought of working on the cooling system of gas turbine because this is the very crucial part because the entire turbine performance and the life of the turbine depends on that. So
yes,
I thought of working on that, sir, and then I thought of developing such kind of blades. But that you can answer. Yes, sir, I tried for developing some kind of internal cavities for the passing of the coolant, but due to the limitation of our lab, I was unable to develop such kind of system. So I thought of to go for some such kind of external cooling system, research related to external cooling system. So आप answer कर दोगे. They also know
yes,
that, and
yeah,
even everybody is going to understand that. है ना? It's a very
yes, sir,
genuine point actually.
yes, sir,
So then, what actually they are more actually interested in knowing the outcomes. They are more interested in knowing the learnings to that particular research. तो
yes,
वो
sir,
तो
yes, sir.
पता होना चाहिए आपको कि internal cooling में external cooling में what kind of results you got and how it can be further we can make it more efficient. Okay.
Yes, sir.
तो आपको जो दिक्कतें आई if those kind of things are there in the literature and if you solved some of the problem industrial problem or
Yes, sir.
any of the issue if you are able to identify then that you need to raise so some
Yes,
of
sir.
the outcomes must be there in your research
Sir.
work you know
Yes, sir.
and
Yes,
you
sir.
need to highlight all those things तो
Sir,
अभी तो
sir.
हाँ yes go ahead
Yes, sir. Sir. Some of the outcomes I can say that, sir, regarding this cooling effectiveness, if we go for the contour and wall, this uh, the area which the coolant cover over the end wall has enhanced because of the implementation of this contoured end wall. And
mm-hmm.
because the secondary means the transverse flow has reduced, and the because of the end-wall contouring, the flow within the boundary layer got more axial momentum.
Mm-hmm.
So because of that involved implementation of the contoured end wall, the more area cover of coolant coverage we has
So what we'll do
observed.
Shushan what we'll do for that
Yes, sir.
now I'm getting the idea
Mm.
because you are we had some discussion in the beginning but
Yes, sir.
before that we have not discussed about that okay
Correct, sir. Yes.
that I think 4 or 5 days ago also when Vijender sir invited me to join some smoke
Yes, sir. Yes. Yes.
in the beginning I was not
Suddenly.
having any idea you know
Yes, sir. Correct.
I got some message and I entered into the meeting
Yes,
this
sir.
time also you appeared and I thought of there is some student coming for some snap mock okay so we
Okay.
had some discussion so what I feel because this is a very specific domain for which you are preparing they
Yes,
want
sir.
some expert who is having some understanding or some research who carried out in the area of
Turbo
gas
machinery.
turbine turbo
Yes, sir. Correct.
machinery
Correct.
cooling system
Yes, sir.
So what we can do, Shushan, you can share your work with me, some
Yes.
PDF or some file if you are having, just share with me. I will go
Yes.
through that. Okay.
Yes, sir. Yes,
And
sir.
then I think we will be in a better, condition to discuss all those things. Fine.
Yes, sir. Yes, sir.
So I'm going to ask you more and more questions related to your work actually, because
Yes,
they
sir.
are actually expert. They are expert in that area. Because there must be some expert there in that area of aero
Yes, sir.
fluid machinery.
Yes, sir. Sure, sir.
Okay.
Yes, correct.
So and you need to be make yourself capable enough to deal with all those kind of questions.
Yes, sir.
So for that, just share that file with me. I will go through the your work. Okay. And then
Yes,
we will
sir.
have some more discussion. I feel fundamental knowledge is fine.
Okay, sir.
You need to be
Sir,
more creative. Some of
no,
the
sir.
cases.
Sir, any questions I answered wrong, sir? Some of the questions I didn't answer,
So
so I need.
yes, yes, yes. Those you need to work on all those things. Like the some of the question I asked you, I think initially I asked you related to the fin questions. Okay, some of
Yes,
the
sir.
question pins and
That rate of
the
heat
shape
transfer,
factor.
sir.
हाँ.
Rate of heat transfer. Rate
Rate
of
of heat
heat.
transfer. अब उसके लिए क्या करना था आपको? You need to develop some case. You can go with, sir, there is a plate. Okay.
Ah,
So or you can consider it kind of plate. It may
yes,
be
sir.
of
Yeah,
any
sure, sure, sure.
shape.
Yeah.
And now you are having some kind of force convection because the fluid is moving,
Yes, sir.
the plate is stationary.
Yes, sir.
So heat transfer is going to take place from both the surfaces.
Yes, sir.
So you can model it like a vertical plate,
Yeah.
cold vertical plate, and then fluid is passing over that.
Yes, sir.
Are you getting?
Yes,
So
sir.
it's like that. There's a cold vertical plate and fluid is passing like over this.
Yes, sir.
So fluid is what? Fluid is the hot one. Plate is cold.
Yes, sir.
Then you can go with some kind of bound layer formation. You can choose some correlations available. You can find out the Rayleigh number. Obviously the flow will be turbulent only because the machinery is moving at a very high speed.
Yes, sir.
So based on that, I feel some of the relationship you can develop fundamental level, basic level. But
Okay,
obviously
sir.
at R&D level, we go with some kind of simulation modeling only
Yes,
based
sir.
on more complex formulations or equations, we can say. But at basic level, you can approach it like that. I hope some idea you are getting how to approach a particular case.
Yes, sir.
Are you getting, Shoshan? So
Yeah,
what
I got it.
actually we are interested in finding out the rate of heat transfer.
Yes, sir.
Then finding out the rate of heat transfer, you can equate it with the MCDT.
Correct, sir. MCDT. Yes, sir.
Whatever coolant is entering, it is entering at some mass flow rate. So suppose you provided some of the cavities. So cavities are already there.
Yes,
You
sir.
also know the diameter of those cavities. So that thing is there. So if you are able to find out the mass flow rate, then you will be able in a position to maintain the proper speed, proper velocity of the coolant, which
Yes,
is
sir.
required actually.
Yeah.
So heat go in steady state, there is no accumulation of the heat is going to take place. Whatever heat is entering, that is going to leave. Because the
Yes, sir.
properties of the blade, they are not those properties, what you can say temperature or other thing, these are not going to change with the time.
Yes, sir.
And that is only possible when there is no accumulation of mass taking place, there is no accumulation of energy or heat taking place.
Yes, sir.
So the heat which is entering, that we need to find out. How we need to find out? For that you need to develop some model.
Okay, sir. Yes.
And whatever heat is entering, that you need to equate with the heat picked by the heat carried by the coolant.
Yes, sir. Yes, sir. MC delta T. Okay, sir. That is the rate of heat transfer happening in the coolant.
Okay.
MCP. Yes, sir. Yes, sir. Yes, sir.
And for that also, developing that because we have considered some blade temperature, some constant blade temperature, then fluid is entering.
Yes, sir. We have to need to keep it the blade temperature constant.
Yes, yes,
Three. Yes.
yes.
So, okay, sir. So,
In steady state, obviously there must be some steady state temperature, no?
yes, sir. Sure.
There must be some steady state temperature because if turbine is rotating, so
Sir,
initially,
for example, sir, if the fluid coolant is entering at some 200 Kelvin, 200 degrees Celsius, and our intention is to keep the blade at 300. So that is so we know the inlet temperature of the coolant and the blade desired blade temperature. So from that, how we will calculate the rate of heat transfer required to keep the blade at 300.
no, you are saying it coolant inlet temperature is known to us.
Yeah, known to us.
Then obviously mass rate, those are the things that we need to control based on the requirement.
Yes, sir. Yeah, how much
So
mass flow rate?
requirement is what? Some steady state blade temperature.
Yes, sir.
how much heat we need to remove. Those are the inputs. Mass flow rate we need to maintain. It is you are actually applying going with the kind of reverse thing. You are saying ki sir, the temperature difference we know, the mass rate we know, those are required. Na? Those things we are going to maintain accordingly,
So
according to the
so
heat.
how I have to start thinking? So I have to, okay, first I
You
have
need to
to
start
calculate.
thinking from the heat, from where heat is going to transfer. Heat is going to transfer from the hot fluid to the turbine blades,
Yeah, yes sir, yes sir.
and
That okay sir.
that we are
Yeah,
removing through the
yeah.
coolant.
Yes, sir. Sir, anyway, if we our intention is to keep the blade temperature or the blade temperature below 300. That is anyway definitely we are sure that, because if it go beyond 300, then it will deteriorate the property. So
Mhm.
so then that I got it, sir. It will happen from the hot fluid to the blade first, then
Mhm.
blade to coolant happening. But anyway, we are our objective is to keep the blade at low temperature of
Yes,
this
yes.
300 Kelvin. So from there, if I am thinking
Mhm.
how much inlet temperature also I know. So what at what?
So
So
for
how
that,
to?
what you can do, like suppose there is a coolant, na, some coolant is available. So for coolant also some kind of cooling system, maybe we are using. It will be
Yes,
some
sir.
kind of cooling system.
Yeah, yeah,
Okay.
yes, yes.
So whatever is the limitation of that, at what minimum temperature coolant is available, that is also known to us based on
Known
the
to us.
atmospheric
Known to
condition.
us. Yes, sir.
We can go with some kind of atmospheric conditions.
Yes, sir.
Okay.
Yes, sir.
So
Okay.
the coolant entry temperature is known to you.
Yes,
Okay.
sir. Sure.
And how much kind of change you want, and the mass rate, what you need to maintain, those are actually we want to find out based on the heat which we need to remove. So you need to
Correct,
find
sir.
out the heat which we need to remove.
Okay.
Okay.
Yes,
And
sir.
that you need to equate with what MCDT.
That, sir, that from convection heat transfer equation we can find or not. HA. We know the cross-sectional area or surface area of
Uh-huh.
the blade or coolant interaction. That area we know, and the delta T also we know.
That also, yes, we can find out. But for that, if you want to use HA delta T equation, you want
Yes,
that.
sir.
So
Yes.
for that, you need to find out some convection heat transfer coefficient.
Yes, sir.
You can go with that also. You
So
can go with
that
that
it,
also.
yeah, if we know the H
For
value,
that H value, for
how to
laminar
calculate
flow, turbulent flow.
H value, how we, yeah,
So
you using correlations.
let me tell you some of the basic case actually.
Okay.
If there is a flow is turbulent, then you can go with the Dietz-Boulter equation.
Which equation, sir?
Dietz-Boulter equation. Generally, we go with the kind of cavities. I hope we provide generally kind of cylindrical cavities only, na?
Yes, sir.
So Dietz-Boulter equation we can use. Okay. Or
Oh,
for laminar flow, again there are some specific cases. It's a constant wall temperature. So that because we are considering the blade temperature constant, so you can go with that case. Laminar flow constant wall temperature.
sir, if I say, sir, Nu is equal to HL by K, and
Mhm.
H can be calculated from Nusselt number into K by L, and Nu we have the turbulent correlation for Nusselt number. So
Mm.
that is dependent on
No,
Prandtl
Nusselt. Actually,
Prandtl.
that we need to first obtain. H first we need to obtain based on the
Yes.
conditions. Huh?
Oh, okay.
What steady state temperature we are maintaining, what is a hot fluid, the coolant fluid entry or exit temperature. So you will be able to evaluate some bulk mean temperature. So at
Oh,
that bulk mean temperature, you need to evaluate the properties of the fluid.
yes,
And
sir.
after evaluating the properties of fluid, easily you will get some H value
Yes, sir.
based on the correlations available. Now, whether it is laminar flow, turbulent flow, easily you will be able to calculate. Those are
Sir.
basic cases. The flow over flat plate, or what you can say, the flow inside pipe.
Yes, sir. So
तो उस हिसाब से
in case of blades, that correlation will work or not?
blades. What?
Blades, in case of blades,
No,
will be
no.
there.
Obviously, it is not going to work.
Okay. So,
So why? Because here we are modeling it like a vertical plate, but actually it is not a exact vertical plate.
exactly.
Second,
Yes.
it's not a kind of static plate. It is rotating.
Yes, sir. Yes, sir.
That's why I suggested you na ki just share the work which you carried out with me, so that I will be able to evaluate ki what kind of data from the literature you have used. Because this research is very much specific now. Are you
Yes,
getting?
sir. Yeah, I got it.
So I am giving you only some kind of fundamental idea.
Yes, sir. Yes, sir. I got it.
And But yes, exactly. I hope some of the researches you referred, which were earlier carried about by various researcher, and you
Yes.
referred to their results, and based on that you carried out some research.
Yes,
Okay,
sir.
so you are having sufficient time. When is your interview?
Sir, I not yet announced the date. So it
Means
will
we are having
happen
sufficient
within 1 or 2 weeks or 3 weeks,
1 or
I
2 weeks.
think.
Fine, fine. So share your work immediately, and I will
Sir,
go through
that
that.
sir thesis, if I'm sharing, can you complete? So I'm thinking which file I will share with you.
Thesis only, thesis.
Thesis will be means it is long. Okay, some 150, 170 pages. Okay, you can go through the result part.
Yes, yes, yes. I will
Just
go through that. Hmm.
yeah. Then, sir, one more thing, sir. Actually, I am not much concentrated to the heat transfer. I focused on the aerodynamic part.
Your work is majorly related to that only.
Yeah,
That's
aerodynamics
why
only.
at end we conclude. Yes, your work is majorly related to aerodynamics.
Yeah, yes, sir.
But you entered into the session and you requested for its transfer snap. That's how we started. Okay,
Yes, sir.
and
Yes, sir. Yes, sir.
I have
Yes, sir.
not asked you. So it is good to go for some sessions, some snaps related to aerodynamics, fluid
Yeah,
mechanics.
yeah.
You are
Okay,
having
sir.
my WhatsApp number now.
Yeah, I have. I have.
We will discuss actually through WhatsApp. We will discuss. We have some more discussion. Good luck.
Okay, sir. Thank you, sir. Thank you.